kind of weird. We're doing one section in Chapter 8. .2a today. And the first example is the limit as x goes to 0 of the sine of 10x divided by 5x. So this is just a limit. It's been a while. I mean, we did a limit towards infinity a couple days ago, but really since Chapter 2, we haven't done a ton of limits. So let's try to jog our memory here. We had a pretty big list of ways to calculate limits. So what was one of them? Yeah.
First one we learned is you can make a table.
Yeah, obviously you can make a table if you have a calculator. That's great. And then, that got kind of annoying, and then we also noted that sometimes we don't have a calculator. So then there were a bunch of non-calculator methods. So what was one of those? Yeah, Sean? That's right. We did limit laws. And limit laws worked great unless there was division and the limit of the bottom was coming out to 0, right? And then that didn't work either. What else? Yes, sir? So then sometimes we could factor things out and stuff would cross out, right? And there were several more. I'm not going to go through them all today. So I'm not sure how many we had, maybe 9. So I'll make this new one number 10. So this is the topic today. This is the new method for calculating a limit. Okay, but before I tell you the name of that new limit, and before we do that new method, let's do this so that we have an idea of what the right answer is, so that this new method doesn't seem like it's hocus pocus. If I just do it the new way and get an answer, you don't have any assurance that that's correct, other than just believing me, but it'd be better if you have some other reason, right? So, okay, so let's make a table here. So just pick 0.1, 0.01, the stuff close to 0. Make sure you're in radian mode, right? Whenever you do sine or cosine or tangent or any trig function in calculus, you have to be in radian mode. We got the sine of 10 times 0.1 divided by. Also make sure you put parentheses around the denominator. 5 times. So I'm getting 1.683. See, check me on that, of course. Those numbers looking okay? So based on this table, it looks like it's getting close to 2. So now we have an assurance of what the answer is supposed to be. And so then when I show you this new method and I get 2, at least you'll reasonably be able to believe that this is the right way to go. Okay, so here's the title. Here's what it's called. It's named after a French guy. His name was Lupital. So this is Lupital's rule. All right, so what you do is you take the limit of the top by itself. And sine of x is a continuous function. So that means that the limit can go past that. Talked about that a little bit in chapter 2. When you have a continuous function, limit can go past the function. And then you do limit laws here. The limit of 5 is 5, and the limit of x is 0. And then 5 times 0 is 0. So this would end up being the sine of 0, and the sine of 0 is 0. So I did limit laws here, right? Okay, so I took the limit of the top by itself. Okay, then I'm also going to take the limit of the bottom by itself. And that's 0. So that means that limit laws would not work on this problem, right? Right here, if the limit of the bottom is 0, that means limit laws are out. So it's good we have this other method. It's good we have these other methods, but in particular today we're going to use this one. Okay, so L'Hopital's rule has some requirements. You have to check. It's a really specialized rule. It works when the limit of the top is 0 and when the limit of the bottom is 0. So the reason I did these limits separately is I was checking to see if L'Hopital's rule was valid to you. For, like with the mean value theorem, you can't use it unless you have a differentiable and continuous function, right? So before you try to use the mean value theorem, you check to see if it's differentiable and continuous, and then you proceed. So same thing with L'Hopital's rule. The limit of the top and the limit of the bottom coming out to 0 means that I'm allowed to use this new method. Okay, so now I can proceed. And the new method, what you do is you take the derivative of the top and the bottom separately. So the derivative of the bottom is 5. And the derivative of the top is cosine of 10x and then times 10 from chain rule. Now this mess here is not the derivative of this, right? Because the derivative of this function would be quotient rule. So this is why we wait a long time to learn L'Hopital's rule, because you have to be really solid on quotient rule before you can. Because for a while you thought that the derivative of this would be this, right? And in fact, since then you've probably made a few mistakes and accidentally did this for the derivative, right? But we're not taking the derivative here of the whole mess. We're just taking the derivative of the top separate from the derivative of the bottom. It's just because that's what L'Hopital's rule asks us to do. Okay, so this function here, it turns out, has the same limit as this function here. So I can calculate this limit instead of calculating this one. That's what L'Hopital's rule says. It says that if you take the limit of this function, it's going to give the same answer as the limit of this function. All right, so now I'm going to calculate the limit of this function, and that's 10 times the cosine of 0 over 5. I did a bunch of limit laws just then, right? And the cosine of 0 is 1. So we get 2. We knew the answer was 2, right? Because the table showed us the answer was 2. So this is a new way to calculate limits. Okay, so now let me write out Lupital's rule formally for you. It says, if the limit of the top equals 0. So a couple things to note here. X doesn't have to be going to 0. It could be going to 2 or 3 or 4. In this example, X was going to 0. But it doesn't have to be a limit towards 0 for L'Hopital's rule to apply. And then I said the words top. So I'm naming this function here f of x. But it's really the top function. So if the limit of the top is 0, and the limit of the bottom is 0, then it turns out that the limit of the top divided by the bottom will give the same answer as the limit of the top's derivative divided by the bottom's derivative. Okay, so let's try this one. Let's say we take the limit as x goes to 1. All right, so we're trying to calculate this limit, and we just learned L'Hopital's rule, so probably that's what we're going to use. But before you're allowed to use it, you have to check to make sure that it meets the requirements, right? This is something we're getting better at, but we're still sometimes shaky on this. Sometimes people are using intermediate value theorem without checking whether you can use it. Some people are using mean value theorem without checking. So same thing with L'Hopital's rule. Make sure you check to make sure you're allowed to use it and show on paper that you've checked before you use it. All right, so you have to take the limit of just the bottom. And you could do a bunch of limit laws, right? And it would end up being 1 squared minus 2 times 1 plus 1. So the limit of just the bottom comes out to 0. That means we now know that we couldn't do this method, right? Hopefully we can do this method, but that'll only occur if the limit of the top also comes out to 0. So we're going to take the limit of the top. And you can do a bunch of limit laws on that. And that comes out to 0. Okay, so this is good news. The limit of just the bottom's coming out to 0, and the limit of just the top is coming out to 0. So that means we can use our new method called L'Hopital's rule. So that means instead of calculating this limit, we can calculate this limit, which will be easier. So we take the derivative of the top and the derivative of the bottom. So according to L'Hopital's rule, the answer to this limit is going to be the same as the answer to this limit. Okay, but unfortunately, if we did the limit of the top and the limit of the bottom, we'd get 0 again, right? You with me? I've already showed that I know my requirements here, so I'm not going to show it a second time. So I give you permission to, the second time it happens, not show the requirements, as long as you show it the first time. But then I'll have to back off on that and make you show it every time if you're going to not do it the first time. You with me? Okay, so does everybody see that L'Hopital's rule applies to this? Because the limit of the top is 0 and the limit of the bottom is 0. So that means that we could do L'Hopital's rule again. So that means this limit is the same as this limit. And then finally, limit laws will work. And the final answer to the limit is 3. So that means that if we made a table for this limit, if we plugged in stuff close to 1, the outputs would get closer and closer to 3. All right. So now we're going to take the limit towards infinity. And, things have been going so well with L'Hopital's rule, let's go ahead and try to use it. So we're going to take the limit of just the top and the limit of just the bottom. And when x gets really big, x cubed is going to get really big, right? So this is going to infinity. And when x gets really big here, x squared is going to get really big. And 2 times x is going to get really big. And so this is going to get really big. So this is going to infinity. So they're not going to 0. But it turns out that L'Hopital's rule also applies if both of these limits are 0. Sorry, I said that wrong. It does apply if both are 0, but that's not the new news. The new news is it also applies if both of them are infinity. It can't be 0 mixed with infinity, though. So if they're both 0, or if they're both infinity, then L'Hopital's rule applies. Okay, so this time, both limits came out to infinity. So that means that this limit is going to be the same as this limit. But unfortunately, this limit is also not working out super good, because the limit of the top is infinity, and the limit of the bottom is infinity. So L'Hopital's rule applies again. And now the top is getting close to 2. And the bottom is getting really big. And if you take 2 divided by a really big number, that's going to get closer and closer to 0. So the limit of this is 0. So that means that the limit of this is also 0. And the limit of this is also 0. Okay. About the limit as x goes to pi of cosecant x over 1 plus cotangent x. So I'm suspicious that perhaps we'll be using Lupital's rule since that's the topic of the day. So I'm going to take the limit of the top and the limit of the bottom separately. So to logic this out, we're going to need the unit circle. So we're getting close to pi. There's pi. That's the point -1, 0. So we're just close to that, though. All right, so cosecant, that's the reciprocal of sine. The sine is the y value, right? So we're getting, the sine is getting close to 0. So it's like 0.1. So the reciprocal of that would be 1 divided by that. So 1 divided by 0.1, which is 10. And then it would get even, the sine would get even closer to 0, right? And be 0.01. And then it would be negative, or sorry, it would be 100 instead of 10. I don't know why I switched to negative. Okay, so as you get closer and closer to pi, this is going to get closer and closer to infinity. Technically, the reason I know why I was thinking negative, but I was thinking ahead of here. Technically, if you come in from this way, it's going to get close to positive infinity. And this way, it's going to get close to negative infinity. But anyway, this is getting really big. That's the takeaway. All right, so now let's think about this. Cotangent, well, the limit of 1 is 1. So really what we care about is the limit of cotangent. Cotangent is, well, tangent is y over x. So cotangent is x over y. So as we get close to pi, we're going to be taking negative, something close to -1, and dividing it by something close to 0. And that's going to get really big. If the bottom is negative, then it's going to get close to positive infinity. If the bottom is positive, it's going to get close to negative infinity. But the point is, something close to -1 divided by something close to 0 is large. I guess I need to acknowledge that it's positive infinity from one side and negative infinity from the other side. So at any rate, this is getting really big. So since the limit of the top is getting really big and the limit of the bottom is getting really big, L'Hopital's rule applies to this problem. Okay, so that means I can take the derivative of the top separate from the derivative of the bottom. So this limit that I'm trying to figure out might be easier. So cosecant is negative cotangent. No, it's negative cosecant times cotangent. Sorry about that. The derivative of secant is secant times tangent, and the derivative of cosecant is negative cosecant times cotangent. Then the derivative of 1 is 0, and the derivative of cotangent is negative cosecant squared. Remember, the derivatives of the cos are all negative. That at least helps you get some of this memorizing done. Okay, so that's kind of nice because then this cosecant is going to cancel with one of those cosecants. So we have the limit as x goes to pi of cotangent of x over cosecant of x. Cotangent is cosine divided by sine. Remember, on the unit circle, cotangent is x over y. Tangent is y over x, right? So that means cotangent is x over y. And x on the unit circle is cosine, and y on the unit circle is sine. So that's how I remember that cotangent is cosine over sine. And then I'm dividing by cosecant, right? But cosecant is the reciprocal of sine. So I'm dividing by 1 over sine. Trig always makes things a little bit tricky. Is everybody okay? All right, so then I'm going to change flip this. So we got cosine x over sine of x times sine of x over 1. And that's really convenient because then the signs cancel. So we're going to take the limit as x goes to pi of cosine. And when you get close, the cosine is the x on the unit circle. So when you get close to that pi angle, you're going to get close to negative 1 on cosine. So see, this limit was tons easier to calculate than this limit, right? That's the power of L'Hopital's rule. It can take a tough limit and turn it into a much easier limit. But don't use it unless the conditions are met. So make sure that the powerful rule, but you can't overuse it. You have to make sure the conditions are met before you can use it. Everybody doing okay?